Hi, my name is Boris Pismenny, and I'll be presenting Schlink, networking with shared receive links. This work is a collaboration with my advisors, Adam Morrison and Dan Tsafrir. So software and NICs interact via logically cyclic arrays called links. When a packet arrives from the wire, the NIC DMA writes it in a buffer pointed by an entry of the receive link. The NIC then marks the entry as done, indicating to software that it is ready for processing. Multiple packets can arrive until software checks the link for packets, and they are all stored in sequence. Software checks for packets starting from the head entry marked in bold. Software reads a batch of these packets, clears the corresponding done flags, and replaces the buffers with new buffers. Then software moves the link's head, indicating to hardware that the buffers can be reused. Finally, software processes the packets. Note that all buffers in the link must be processed before any of them can be reused. By default, receive links have 1,024 entries. Each entry has a buffer large enough to hold the maximum transmittable unit on the network, which is about 1.5 kilobytes. So a network-intensive application would use a working set of about 1.5 megabytes. For scalability, today's multi-core CPUs use a link per core, and the NIC distributes packets between cores using an RSS hash on packet headers. Hence, when running network-intensive processing on n cores, the total working set consists of all receive link buffers of n cores put together. Namely, the working set is n times 1.5 megabytes, which today is often greater than the last level cache of Intel CPUs. This is important because, as we will show later, working sets greater than the last level cache degrade performance when NICs have direct access to the last level cache, such as with Intel DDIO. In this work, we propose to replace per core receive links with a shared receive link, which we call Schlink. With Schlink, the working set is only 1.5 megabytes, which fits in the last level cache. Schlink helps applications when the impact of LLC contention caused by I/O outweighs the overhead of synchronization on the shared link. To show the cause of a large working set, we run an experiment with a synthetic network function that receives packets, accesses memory twice per packet, performs routing, and sends the packet out to the wire. We run this network function on all CPU cores and load it with 200 gigabits per second using an open loop load generator. The following figure shows memory bandwidth as a function of link size. We see that links smaller than 128, whose working set fits inside the DDIO portion of the last level cache, have less than 20 gigabytes per second memory bandwidth. Next, we see that links smaller than 512, which fit in the last level cache, but not in DDIO's portion of the last level cache, have less than 40 gigabytes per second. Finally, with links of 1,000 entries, which is the default or larger, the working set exceeds the last level cache, and all data goes through DRAM. So smaller links cause smaller working sets, which improve memory bandwidth. But memory bandwidth is only a secondary metric. What about throughput and latency? So when looking at the throughput of the same experiment, we can see that small links reach line rate speeds of about 200 gigabits per second. Larger links, whose working set exceeds DDIO, have up to 20% lower throughput. This is caused by high memory bandwidth, which slows down both the NIC and the CPU memory accesses. Because working sets that fit in DDIO achieve line rate throughput, they have the lowest latency of about 100 microseconds, but the latency of larger working sets increases proportionally to the link size. This happens because the rings of network functions that fail to meet line rate fill up with packets, and as a result, the latency experienced by each packet is the sum of the latencies of processing all packets waiting inside the link. So since the link size today is 1,000 entries, and we saw that smaller links improve performance, should we just use small links to solve this problem? We find that small links are impractical, as we show next. We run an experiment with DPDK's layer 3 forwarding, and we measure the maximum throughput attainable without loss for various link sizes. When we run the experiment with traffic spread among multiple calls, we see that we can reach line rate with any ring size. But when we repeat this experiment with all traffic directed to a single call, we find that rings smaller than the default degrade performance, while rings larger than the default do not improve it. This suggests that the default size should be maintained. We ask ourselves whether sharing the default size ring would solve the problem we observe with the no drop throughput. So we repeat the same experiment with the shared default size ring, and we consider both single core and multi-core performance. The leftmost points correspond to the default ring size per core, which we saw in the previous slide. As we move to the right, the number of cores sharing each default size ring increases with no loss to performance. Meanwhile, the working set size decreases by up to 8 times on the rightmost point. So now that we've motivated the need for sharing rings, let's discuss how we share a ring. So the naive approach to share a ring uses a lock to serialize access to the shared ring. When packets arrive from the network, all are placed inside the shared ring. Calls contend on the shared ring's lock. And once a call acquires the lock, it reads a batch of packets, clears the done flags, replaces packet buffers, and advances the head. And finally, it releases the lock and processes the packets. Then another call would do the same. The problem with this approach is that we have serialized ring polling and packet processing, which is undesirable. We solve this problem by separating polling from the shared ring. So instead of polling for packets on the shared ring, calls poll for packets on a per-call completion ring. When packets arrive from the wire, the NIC DMA writes them to the shared ring and sets done flags in the completion rings selected according to the RSS hash of packet headers. Calls poll in parallel on their corresponding completion rings for packets, read a batch of packets, clear the done flag in the corresponding completion rings, advance the completion ring's head, and replace the consumed shared ring buffers. But synchronization is still necessary to advance the shared ring's head. So one of the calls will acquire a lock, meanwhile others will make progress. Finally, the call with the lock will advance the shared ring's head, release the lock, and complete packet processing. So completion rings allow for parallel polling and packet processing. But since completion rings enable calls to process packets in parallel, packets may be processed out of ring order. And sometimes a call cannot advance the head even though it reposted its buffers. For example, when packets arrive from the wire and call 1 makes progress while call n is busy with other tasks, then call 1 will try to advance the head before call n read its packets, which cannot be allowed as it will let the NIC override packets of call n. Hence, call 1 must leave the head as is, and later call n will examine the completion ring and make progress. But since call n is unaware of the packet processed by call 1, its update to the ring head will be 1 entry short, and the resulting head position will become stale. So to solve this problem and make head advance correctly, we need to track process entries in the shared ring as we show next. Following the previous example, when packets arrive from the network and call 1 makes progress while call n is busy, then call 1 will try to advance the head, which is forbidden. So instead, call 1 will mark the shared ring's entry as done and finish its packet processing. Later, call n examines its completion ring and makes progress. It will also mark the process entries in the shared ring as done. And check that starting from the ring's head for the done indication to see if it can advance the head. It will clear the done markings and advance the head accordingly. And finally, complete packet processing correctly. So while using shared rings, we found that besides the cost of synchronization and lock, shared rings can degrade performance due to the lack of isolation between calls. This can happen if, for example, a call is persistently slow, either due to excess traffic or due to processing overload. We call these conditions pathological. To demonstrate a pathologically long processing condition, we use our previous example, where packets arrive from the wire and call 1 makes progress, while call n is busy. But this time, call n will continue to be busy after call 1 completed its processing. So when future packets arrive from the network, they will be placed in the ring until eventually the ring is full and new packets that arrive from the network are dropped due to lack of space. So to address pathological conditions, we switch between shared and private rings dynamically. We enable ShRing when it helps, that is when cache contention is high, as measured by Intel PCM. We also disable ShRing when it helps performance, that is when there is a call whose load is persistently extreme compared to the rest. We implement ShRing on NVIDIA ConnectX 5 using minor firmware changes that are now generally available. Our implementation is 20 to 100 lines of code, mostly in the PDK's driver layer. This allows applications to enable ShRing without changes to the application logic. To evaluate the performance of ShRing on a real application, we use a stateful load balancer network function. This application relies packet headers to spread load among 16 servers. We run this application on all cores of our server and load it with 200 gigabits per second. We compare between a default size private ring per core, small private rings that fit in DDIO but will cause loss if traffic is bursty, and a ring shared by 8 cores. The working set of private rings doesn't fit in DDIO, and hence its throughput is low. On the other hand, small private rings and ShRing fit in DDIO, and hence they reach line rate, improving throughput by up to 20%. When looking at latency, we see that the default private ring, which do not reach line rate, have latency of 1 millisecond, while small private rings and ShRing have a latency of about 100 microseconds. Finally, we look at the performance under pathological processing skew. To that end, we run a synthetic network function on all CPU cores, where each core accesses memory twice per packet, except one core, which we call the target core. On the target core, we vary the number of memory accesses between 0 and 300. And we load our application with 200 gigabits per second that is spread evenly among all cores, except the target core, which receives only 1% of all traffic. In the figure, we plot the throughput of our application as a function of the number of memory accesses on the target core. With private rings, the application cannot achieve line rate because its working set is too big, and it performs similarly regardless of the load on the target core. This is expected because 99% of all traffic is being processed by cores other than the target core. In contrast, for ShRing, it achieves line rate when the overhead on the target core is low, but when load on the target core exceeds 100 memory accesses per packet, ShRing performance starts dropping. This happens because the slow target core prevents other cores from making progress. Dynamic ShRing solves this problem by identifying the persistently slow core and switching to private rings. In conclusion, too many receive ring buffers degrade application performance, and using small rings cannot address this problem. We show that sharing ring buffers solves this problem despite the synchronization overhead. Thank you.